We present Unimotion, the first unified multitask model for flexible motion control and frame-level human motion understanding. Our goal is to unify multiple tasks into a single human motion model, which is capable of taking in sequence-level text, human motion, frame-level text, or any combination of these inputs, or none in the case of unconditional generation. Unimotion generates corresponding human motion or frame-level text for motion understanding. With this model, we unify tasks treated separately by prior works. Specifically, prior works focus on the single task of generating motions given sequence-level texts, such as MDM, MLD, and motion diffuse. Some other works can take frame-level text as input and convert them into motions, such as FlowMDM and STMC. For motion understanding, current models such as Motion GPT or Motion LLM can translate motion into sequence-level text or perform question answering based on the given motion. Our model, on the other hand, unifies all these tasks into a single model, allowing for multi-model input. In addition to previous works, our model can perform several novel tasks. Specifically, our model can generate motion based on both sequence-level text and frame-level text, enabling fine-grained motion generation while also being stylized by the sequence-level text. Unlike current models, such as Motion GPT and Motion LLM, our model understands human motion both semantically and temporally, translating motion into frame-level text with durations. Finally, given pure noise, our model can jointly generate human motion and frame-level text. Our model is a transformer and trained via denoising diffusion. Motion, frame-level text, and sequence-level text are the inputs. The text is encoded using a clip model. Motion and frame-level text are aligned temporally via concatenation. Inputs can optionally be noised, as commonly done in diffusion. The inputs are fed through a transformer-based model. To allow for true multimodal diffusion, we propose to use two different diffusion time steps for the motion and the frame-level text, Tx and Ty. Due to the separate time steps for motion and text, we can flexibly sample using pure noise, clean motion, clean text, or any combination of these. This allows for flexible input of any combination of sequence-level text, frame-level text, or motion data during inference. Our model is trained to output clean motion and frame-level text annotations. The model is trained with two loss functions, tailored for motion and frame-level text. Here we present the experimental results demonstrating our model's multitask capabilities. We show our model can be controlled via both sequence-level and frame-level text, while prior works can't. While FlowMDM can be controlled by frame-level text, it does not allow to specify sequence-level text at all. STMC, on the other hand, allows to specify sequence-level text additionally to the frame-level text. However, we see the frame-level text is ignored for the generation. On the other hand, our model allows for control from both sequence and frame-level text. Next, we visualize sequence-level text-to-motion generation. MDM can only output the corresponding motions. Our model not only generates motion, but also outputs the corresponding frame-level text annotations, unifying motion generation and understanding in the output. Our model enables tasks no prior work can perform. For example, motion-to-text generation with temporal alignment. Here we generate frame-level text for an unseen motion capture sequence. Given motion, our method outputs text labels for atomic motion per frame, achieving fine-grained motion understanding with temporal awareness. We use our model to annotate 2D videos from YouTube. First, we apply existing methods for 3D human pose estimation. Our model can then label the motion to generate per-frame annotations for the video. By combining various tasks with our multitask model, we can further achieve applications such as motion generation with editing control. In this example, the first task is sequence-level motion generation. Given a text prompt, we can generate both the motion and the frame-level annotations. We can then perform editing tasks, such as replacing walk forward with jog forward. By conditioning on the updated frame-level text, the model can output the edited motion, replacing jogging forward with walking forward. Moreover, Unimotion is the first model to achieve unconditional joint generation of motion and text. By conditioning on pure noise, we can simultaneously diffuse both motion and frame-level text, producing novel aligned motions and frame-level annotations.